Matrix multiplication also has some convenient properties. Here we're assuming that A, B, and C are matrices and that little a and little b are scalars. First of all, property number one tells you that when you're multiplying three matrices together, you have a choice in the order of which you're multiplying them. You could multiply the last two matrices first, and whatever you get, multiply times A. Or you could multiply the first two matrices first, and whatever you get, then multiply it by C. So this comes in handy sometimes when you have three matrices multiplied times each other, and because of whatever numbers you're given, it might be easier to start with this product or that product for convenience. So you have those choices. What this property is not saying, it's not saying that you can take any one of those matrices and rewrite them anywhere you like. So you cannot reorder their position in the product. What this property is saying is that you can multiply the pairings in different orders. Property 2 is really convenient when you're working with matrices with a lot of fractions. So it's saying that if you have a matrix with a scalar that might be annoying, like a fraction or some radicals, and you have another matrix with the same kind of structure, you can factor out those annoying fractions and radicals to the forefront and leave behind the product of matrices that might be a lot easier to manage. Let me give you an example. So let's say we have radical 2, negative radical 2, a 3 radical 2, a 5 radical 2, times a 1 over 7, 3 over 7, negative 1 over 7, 5 over 7. So from the first matrix, I think you can agree the radical 2's are getting in my way. I can factor them right out, leaving behind 1, negative 1, 3, 5. From the second matrix, the 1 over 7 is kind of getting in the way. When I factor those out, I leave behind a 1, 3, negative 1, 5. So notice that the product that's left over is a whole lot easier to manage. Not a fraction, not a radical in sight. And then once I get this simplified, then I'll think about bringing these guys back in, right? But in the meanwhile, they're waiting outside, just waiting for me to take the product of these two matrices. Properties 3 and 5 are telling you that you have a nice distributive property. When you have an A multiplied times a sum, you can take the A and distribute it from the left-hand side. Or when you have a matrix A multiplied on the left-hand side, you can distribute that in. And what I would have you consider is the position of those A's. In this case, since the A is on the left-hand side, when you're distributing it, the A's, no, I said it wrong. When the A's are being multiplied on the right-hand side, when you distribute them, the A's stay on the right-hand side. And when the A's are being distributed from the left-hand side, when you distribute them, the A's stay on the left-hand side. That's really important. And again, that follows from the fact that matrix multiplication is not commutative, right? So if we were to have written this as BA instead of AB, it would make a big difference. For property 5, we are referencing this matrix I. So the matrix I is a matrix made up of the number 1 along the main diagonal and zeros elsewhere. So if you're talking about 2 by 2 matrices, the matrix I is going to be the matrix with ones along the main diagonal and zeros elsewhere. If you're talking about 3 by 3 matrices, the matrix I is going to be the matrix with size 3 by 3 with ones along the main diagonal and zeros elsewhere. And so on for 4 by 4s, 5 by 5, 6 by 6s, right? And these matrices are called the identity matrices. And what's important about these identity matrices, one of the things that's important about identity matrices is that when you take an identity matrix and multiply it times A, you get A. And when you take a matrix A and multiply it by I, you get A. So whether you multiply a matrix on the left-hand side or on the right-hand side by these identity matrices, you get the original matrix that you started off with. Later, we'll be using these identity matrices to find something called an inverse matrix. So in the structure of matrix addition and multiplication, that identity matrix is almost like the 1 in the real numbers. And the last property is probably the easiest one to digest. When you take a matrix like 1, 2, 3, 4 and multiply that by the 0 matrix 0, 0, 0, 0, you're going to get the 0, 0, 0, 0 matrix. And this works whether you're multiplying in this order or if you were to reverse their order.